Hey, welcome to chapter 2. This is relations and functions. We're going to look at quite a few things in this chapter. We're going to start with section 2.1 on functions and continuity. We're going to way through learning how to find the extrema, the turning points, the end behavior, and why graphs are the way they are. Eventually being able to solve equations by graphing. That's where we're going in this chapter. 7 sections. We're going to be done with this in 2 weeks. Less than 2 weeks, really. As we go through. So let's look at section 1 here on functions and continuity. So your two objectives, you'll be able to determine whether functions are one-to-one or onto, and determine whether they're discrete or continuous. And this all falls under this standard of FIF4, interpreting the key features of a function, modeling the relationship between two quantities in algebra in graphical or tabular form, and being able to sketch them. All right, so we look at some definitions here first. One-to-one function. A one-to-one function is a function where each element of the domain pairs with exactly one unique element of the range. And we talked about mapping diagrams in Algebra 1. You should remember these, having x's and y's. And so if we put some elements in our domain, and we put some elements in our range, and we can just use numbers. Let's go 5, 6, 7, and 8 here. What it says is that each element of the domain pairs with exactly one unique element of the range. And so like 1 compared to 5, and 2 compared to 7, and 3 compared to 6. But the key is that we have some leftover elements sometimes in one-to-one. And so we're going to talk about that more in a second. But the real key to one-to-one is that every x has only one y. Okay? And again, we talk about functions as being functions, right? So we talk about every x having one y, but remember they are unique. So there's no like 1 and 2 both going to 5. And we'll talk more about that in a second. So onto is a little bit different. So if I have a similar setup here, let's say I've got 1, 2, 3, and 4, and I've got 8, 9, and 10 over here for my x's and my y's. And so what onto says is that a function where each element of the range corresponds to an element of the domain. It doesn't have to be unique. So I could have 1 go to 8, and 2 go to 8, and then 3 go to 9, and 4 go to 10. The key is that every x has some type of y. And so most functions are onto automatically because the key is here that all of our range has something in the x. So again, our arrows go from x to y, but when we're talking about onto, we're looking at the y's and making sure all of them have something pointed at them. If we go back up to our first example, this first one is not onto because of this 8 here. So again, this one in the first example is one-to-one, but not onto. Our one down here is onto, but not one-to-one. And so let's see what a function would look like if it was both onto and one-to-one. So we'll draw our diagrams here. And I've got, let's say, 7, 8, and 9 over here. So here's my x and here's my y. The key to one-to-one and onto, so it has to be both, is that every element of the x has exactly one unique element of the y. And every element of the range, the y's, has a unique element of the range, or of the domain. And so again, the key is that everything has its own. Every x has its own y, every y has its own x, and nobody's left out in the cold. There's nobody sitting off the side and be like, hey, look at me, I need something here. So let's go look at some examples of domain and range, and then also determine if a function is one-to-one, onto, both, or neither. And so in example 1 here, we've got this little graph here. You'll see that there are 1, 2, 3, 4, 5 points on it. And so as we look at those points, we're going to talk about the domain and the range of this graph. And so when we talk about the domain, remember domain is the x values, and so we're going to list those x values. So I've got -4, and -3, and 0, and 1, and 3. And so when we're just given individual points on a graph, and we're going to talk about that, a terminology for that here in a moment, but we're given individual points on the graph, we list those individual x values in the domain, and we do the same for the range. So we're going to list our y values. And so I've got to pair them at -2. I've got one at +1, one at 2, and one at 3. And so the question becomes, is this one-to-one, onto, both, or neither? Because there are some functions that are neither definition because they've got gaps in them and they're not one-to-one, or they're not onto because every y is not paired with an x. And so we look at our bubbles here and we set them up, so -4, -3, 0, 1, and 3, those are our x's, and our y's, -2, 1, 2, and 3. And we look at our arrows here. And so -4, so when x is -4, I'm going to -2, so this one goes straight across here. And when x is at -3, I go to +1, so that's going here. And when x is 0, I'm going to -2, so I've got an arrow coming back up this way. And when x is 1, I go to 2. And when x is 3, I go to 3. So let's go back to our definitions. Let's kind of review here. Remember, to be one-to-one, a function where each element of the domain pairs with exactly one unique element of the range. So I should only have one arrow coming out of every x going to one single y. Remember, it's not a function if I have two arrows coming out of the same x value. But if we look here at -2, I've got -4 going to it, and I've got 0 going to it, so this is not one-to-one. Is it onto? Remember, that's where every element of the range has a element of the domain. And so again, a function where each element of the range corresponds to an element of the domain. There's nothing in that definition that says it has to be unique. And nothing that says that it can only be one value. And so is it onto? Absolutely. And so this function is onto. And so again, the best way to determine these is to look at either the graph itself, and we'll talk about a couple ways that we can do that in a second, or to look at the mapping diagrams of the two domain range. And so as we go on, we look at the vertical line test. It says if no vertical line intersects a graph in more than one point, then the graph represents a function. This should come from Algebra 1, again, just reminding you of this fact. And so like if I go back to this graph, and can I take a vertical line anywhere on this graph and hit 2 points at the same time? If I can do that with any vertical line, or no vertical line, right? No vertical line does this, then the graph is a function. But if there's even one case where it happens, and that's what the second statement here says, if there's any vertical line that intersects a graph in 2 or more points, the graph is not a function. So again, we're just defining what is and what isn't a function based on the graph. But there's a second test we want to introduce here, and this is the horizontal line test. This one's going to be important to us. And it says this: if no horizontal line intersects a function in more than one point, then the graph represents a one-to-one function. So again, can I draw any horizontal line, not a vertical line, but a horizontal line? And so can I take a horizontal line across the graph and only hit 1 point? And again, that's everywhere in my range that I'm looking at this. And so if there's even one line, like the brown line I draw here, so if there is a horizontal line that hits twice, then is it one-to-one? No, because that would be the converse of the statement. All right, so let's look at graphing relations. This should be super simple. We're talking about graphing y is equal to 2x minus 3. Just going to do a quick little sketch here. And so for those playing at home, let's graph this up. Y is equal to 2x minus 3. So we've got -3 as our y-intercept. We're going to go up 2 and right 1. And so we get a graph that looks like so. And remember, as many points as we need to draw our graph. And so remember, y equals 2x minus 3 is just a line. And so is this a function first? And if it is a function, is it one-to-one, onto, both, or neither? And state whether it's discrete or continuous. Now, we haven't talked about those terms. Those terms are actually just a little bit further in our definition, but we'll talk about those in a second. So let's start with function. So is this a function? Well, does it pass the vertical line test? Can I take a vertical line everywhere and see that it is a function? Yes. So this is definitely a function. Is it one-to-one? Does every x, remember what the definition was if we scroll back up, right? Does every x pair with one unique y? Is there ever a point where a y value has two different x's, right? And so remember we said we have a check for this, the horizontal line test. Is there any horizontal line I could draw and get 2 points at the same time? The answer is no. So this is one-to-one, check. Excuse me. And so now we go to on2. Is this graph on2? Remember, to be on2, every element of our range has to have some element in the domain. Well, that means we have to determine what is the domain and range of this, right? So, and that was one of the questions. What's the domain and range? Well, the domain of this function is that this line's going to go on forever. And so the domain is all real numbers. And if we look at this graph and we look at the y values, this graph's going to go forever in y as well. And so it's all real numbers. Now, a couple of notations we want to just talk about. We could use this all real number notation, or let's talk about interval notation for a second. And this is something that in chapter 1 we probably should have hit, but we didn't. So interval notation. And what's going to happen here is when we're all real numbers, it's going to look like this. It's going to be from negative infinity to positive infinity. And what this interval notation tells us is the values that a domain or range goes from and to. And we'll use either parentheses or brackets, and I'll talk about brackets a little later on when we need them. And so the range of this function is all real numbers, so it would again be from negative infinity to positive infinity. Now, if we ever use an infinity symbol, always use a parenthesis in interval notation, because that is an open-ended endpoint, because there's really not an endpoint. We're going on forever and ever and ever. So the question comes back to, is this on 2? Does every element of the range have an element of the domain? And yes, every element of the range here, which is all real numbers, does have at least an x at some point. And so is this on 2? Absolutely, it checks. And so this is both 1-to-1 and on 2. Now let's talk about discrete and continuous. We're going to scroll down in our notes just for a second here and look at these two definitions here above example 4. So a discrete function is a function that has breaks in the domain. And so an example of discrete function would be ones that just have integer values like 1, 2, 3, 4. We can just graph those certain points. The first graph we had drawn up with just the individual points is an example of discrete function. It was a function and it's just breaks in our domain, especially when we look at the graph. A continuous function has no breaks or gaps in the domain. And so a continuous function doesn't necessarily have to go from negative infinity to positive infinity. It can be continuous about a particular domain from, let's say, like -5 to +5. But the key is that in that domain, it can't have any breaks in it. And so let's come back up to our function here. Is this discrete or continuous? And the key to just seeing that is, does it make one nice solid piece as our graph? And so our graph is one solid line, so yes, this is continuous. Again, what would make it discrete is if I had a break in the graph, and we're going to talk about piecewise functions later on in the chapter as well. And so we'll talk about those and how they're either discrete or continuous in their own instances. All right, example 3, evaluating functions. This should be super simple. This is Algebra 1. And so, for example, A, we're going to plug in -2 into this function. So we get f of -2 is equal to -2 to the third minus 3. And so we're going to get -2 cubed, which is -8. And we subtract the 3. And so -8 minus 3 is -11. And so remember, when you're doing function notation, this is how it should look. Remember, f of -2. And really, we should keep the f of -2 on the left-hand side on every line. If you just drop it down with an equal sign and then pick up the f of -2 at the very end, it's not the end of the world in the math sense, as long as you understand that that function is what's on the other side of the equal sign. And so in this case, we get f of -2 is equal to -11. And remember, that relates to an ordered pair as well, that it would be the ordered pair -2, -11, because on this graph, that's where we would find the point. Because remember, this is your x value and this is your y value. Now, sometimes functions that we plug into don't always just give us a number, but some type of expression. And so we can do an expression as well. So we're doing f of 2t here. And remember, everywhere I see the initial variable, I'm going to replace it with whatever I'm substituting with. And so in this case, it's 2t. And so I've got to do 2t cubed, and remember, the cube will go to both the 2 and the t. So 2 cubed is 8, t cubed is still t cubed, and the minus 3 is sitting out back all nice and happy. And so f of 2t is equal to 8t cubed minus 3. Okay? So we already talked about discrete and continuous. And so let's go to example 4. Looking at the table here, we're looking at some EPA data of fuel efficiency for a particular SUV. And so we're going from the years 2001 to 2007. And it says graph the information to determine whether it's a function and if it's discrete or continuous. And so we're just going to draw a little sketch here. No need for a complicated graph, but we'll start with 01, 02, 03, 04, 05. I've run out of room. 06 and 07. And you'll see that our values are in a really tight-knit range in the low 20s, right? And so one thing I want to show you real quick, a little trick that we can do with graphs, is we'll throw in this little break symbol, and that means we're just jumping our graph. And so we're going to go to 20, and then here's 21, and here's 22. Now, just a little side note real quick. You see this little break here that we talked about? A lot of statistical data will use this, and it will actually throw your eyes off when you're trying to compare like bar graphs or line graphs. And they do that intentionally to skew what you're looking at. And so something could be really close to each other, but if they throw the scale off and all they're looking at, like here is 20, 21, 22, it looks like it's such a huge difference. But when we're talking, let's say, population data, and our population's gone up like 2 million over a 10-year period, whatever it might be, but we're comparing it to 330, 340 million people living in the United States. So is that really a big deal? Meh. And so you got to pay attention to those little tricks that statisticians will use. And so we're going to plot this data here. So 20.8, so we're about here. And 20.6, that'd be a little lower. We're back to 20.8 and 20.9, so we're just a hair higher. 21.6 this year, ooh, a lot of gain there. And then 22.3, so we're here. And then 22.6. And I probably should have put a 23 up on this graph so that way we're not too high. And so here's my 7 points that were given. And so the question is to graph it. We've done that. Check. Determine whether it's a function. Remember, function would be that every x has only one y. And so vertical line test, it passes the vertical line test. So is it a function? Yes. And so is the relation discrete or continuous? So the point is, would this make one nice line here or not? I could connect the points, and again, statisticians will do that. But when we're just looking at the data itself, this is a discrete graph because they are individual points along our domain that are broken up. Again, to be continuous, we would need a continuous region that this would just be graphed, and it'd be a nice line or curve that we would have. Okay. We could ask some other questions here if it was 1-to-1 or on-to as well. I'll save that for you if you want to think about it. If it's 1-to-1 or on-to, think about the definitions. Does the table and does our graph meet those definitions? And so as we look at example 5 here, a metro train ticket costs $5.25. The cost of taking a train x times can be described by the function y equals 5.25x, where y is the total cost in dollars, and of course x is the number of times we took the train up here. Determine whether the function is correctly modeled by a discrete or continuous function and explain your reasoning. And so as we think about y is equal to 5.25x, if I just think about graphing that function, we would normally draw a line, right? But here's the key is we're not just dealing with just a line in coordinate space. We've got to think about what we're actually doing with it. We're buying what? Metro tickets. And so would it make sense when I draw this line, when you think about the four-coordinate plane, and we get, 1 and 5.25, so we're here, and then be at 2 and 10.50, right? And so my line would come all the way through like this, through the origin, of course. My graph's not perfect. But would a point like here at 1.5 make sense? Can you buy 1.5 train tickets? No, and so when we graph this function up, it's not going to include all that. It's not going to come down here, right? Because can I buy negative train tickets? No. And so what we're going to get is that this just continues on. Next one would be at 1575. So my next point would be up here. And so the points look like they make a line. I wouldn't have anything in any other quadrant other than quadrant 1 because I can't have negative tickets or negative cost. So this type of function would be what? Discrete. because again, there are gaps in our domain as we go from one value to the next. It's not a continuous piece. Okay, and so as we explain our reasoning, the reasoning is because you cannot purchase, so again, it's discrete because you cannot purchase parts of a ticket. Okay, and so that is 2.1 on just in continuity. And so, like always, if you have questions, ask. Your assignment is in Google Classroom, and I hope you have a great day.